As far as studying goes, um, like I said, I didn't write any notes down, but studying, there are techniques for that. Always studying in the same place. You find your study spot and you go there. Typically, if you're sitting on your bed studying, um, your brain tends to go to the place that it's physically located in. And so if you're in bed, well, there's two things, right? You're either going to sleep or do something else, but that's where your brain is going. Um, and it's not saying, "Oh, this is study time." And so if you have a little quiet spot for yourself, and you have to get out of the house or go somewhere, me personally, when I was studying a lot, I would actually go to a coffee house, and the din, as long as it wasn't too loud, the din of noise around me actually helped focus my thoughts. And then I had something every 5 minutes. At the most, I would take a break. 5 minutes, that's all I would do is for studying. I just look up, and the nice thing about the coffee house is I could just people watch for a few minutes and then get back to it. Literally 5 minutes at a time. If you're studying nonstop for half an hour, you're doing it wrong. You have to give your mind a little time to break. And trust me, it's still noodling around inside of your brain, but you have to give yourself lots of little breaks when you're studying. Um, so breaks has to be the right place, whether it's completely silent like a library, or if you have some music or some noise around you, that doesn't matter. The music and the noise can't be too much, of course. Um, it overwhelms your brain. Um, and a lot of it. And every day, I should say, rather than a lot. It does take a lot of study, but it takes chunks of time. If you say, "Oh, good, it's Sunday afternoon. I have nothing to do for the next 6 hours. I'm going to do all of my studying for the week." Well, good luck. It's probably too much. So, like I said, I really didn't prepare anything for studying. I'm more concerned about testing and trying to maintain your sanity while you're taking a big test. So, first thing I want you to do, and this is pretty obvious, everyone knows this, but when you sit down, take a moment, breathe. Breathing is, um, there's a reason why people who meditate concentrate on their breathing. If you breathe relatively deeply, relatively slowly, you'll calm your brain, you'll calm your entire body down. And so it does affect your physiology. So take the time to breathe. Stay calm. Don't say to yourself, and I hesitate to even say it now, but don't say to yourself, "Okay, don't panic." Don't tell yourself what not to do, because that's what you'll end up doing. When you say don't panic, panic is now in your brain. So, okay, stay calm, stay calm, stay calm. If I don't get it, if I don't get this question, just move on to the next, move on to the next. So even if the first 10 questions you're not sure about, the first 10 questions, now anyone in their right mind would start to panic. Don't do it. So I want you to, okay, that's all right. That's all right. I'll just go back to these. And when you do go back to them, your brain, while you're going over these questions, and I would actually suggest answering them, but still marking them, making sure you go back. But go ahead and answer them. Because as you go on, and now you're on question 30, your brain's still on those first 10 questions, whether you know it or not. It's somewhere in the back of your brain. It's still working that out. And suddenly you might have a spark of going, ah, or you might see something later on in the test that reminds you of something, and then you can go back and fix it. But definitely use the function on the test. If you have a function like right on your computer, and for the SPI you will, of marking the question, something that you want to go back to. Keep moving forward. And I kind of already mentioned this. Keep moving forward. Don't get on the question number 3 and you're having a hard time with it and you're stuck on it for 5 minutes. No. Don't sit on a question for 5 minutes when you have 160 more questions to answer. Move forward, mark it and move forward. Your brain will continue to think about it, and follow-up questions can give you hints. So you have a follow-up question, and by the way, yeah, right here. Remember, if you keep seeing the same question asked again and again, perhaps, oh, you know what? Oh, I'm recording. Let me hide that for now. Okay. I'm only on one screen today, guys, so I don't have a lot of room to have everything up. So if I'm not answering your question, go ahead and give me a ring on my phone. Well, at least I should be able to see it off the corner of my vision. All right, so if you keep seeing the same question over and over again, asked a little bit differently, they'll ask it this way, they'll ask it in the same question but in the negative, that probably means you got it wrong. So think about, stop and say, okay, I keep asking me about pulse repetition frequency. I got something wrong on pulse repetition frequency. So that's actually a really nice hint for you to go back and find that question. Hopefully you already marked it. If you didn't mark it, then you have a little harder time finding it. But that gives you a hint. It also not only gives you a hint that you got it wrong, but the question keeping, there's going to be a wording to the question that suddenly you go, right, that's exactly how it was said in the book. Now I understand what they're asking. Yeah, now I can go back and answer those other 2 questions because now I get it. So strategic, you got to keep you got to just keep in mind that you've probably already had a similar question, or a question that can be answered by the answer that you have right now, the thing you're working on right now. Pulse repetition frequency is the inverse of pulse repetition period. That reminds me of another question. Let me go back and check my answer for that. And so that was, let's see, that was all number 3. Number 4, oh, by the way, and that's because that's how I was thinking about it. Oh, no. Careful with your mind dump. And I'm going to talk about this again. I have a little kind of an illustration of what things you might want to write down. So the mind dump, that's when you go in and you have your little piece of paper that they give you, or whiteboard, and you write down every fact, every equation. If you could remember how to write down every equation, then you don't need to. If you try to write every equation because you crammed right before the exam and your brain goes blank, which it will, you will begin to panic. So be careful how much you want to write down. And I have, like I said, I have some examples of maybe things that are so basic that you will write down, and other things that are not needed either because they're so complicated. The chances of someone of the SPI asking specifically that question is pretty low. So it might not be worth memorizing or trying to cram that down. Or you can derive, like the 13 microsecond rule can be derived in a couple of ways. So anyway. So yeah, if you try to write everything down and then you draw a blank, now you're in panic mode. So be careful with the brain dump or the mind dump. Complicated equations. Memorizing is great if you can. Personally, I can't. I don't memorize equations. You might have noticed that sometimes I'll have to stop and quickly look at my notes because it's because I also get, it's like test anxiety, except I have it every day when I'm teaching you guys. I get anxiety and I forget easy stuff, but that happens to me too, you know, but I've learned how to, for the most part, control it. But if you could memorize the equations, that's wonderful. It's more important to understand what they say. Just remember that. No one's going to ask you without a calculator to work out a complicated equation. Possibly like a very simple equation, 2 + 2, but nothing complicated. That doesn't mean you don't need to know the equation, though. It's really important that you understand the equations. And that's why I use arrows, arrow up, arrow down, that kind of stuff. All right. Number 5, kind of repetitive, be strategic. All good test takers are strategic, or they're brilliant, one of the two. But if they're brilliant, they probably are. They already know how to be strategic without having to think about it. They just are. So most of your questions are going to be multiple choice or true false, which scares people more. So slow down and look at the question. If 2 answers contradict each other, one, not necessarily, because it could be 2 contradictory answers that have nothing to do with the real answer. But oftentimes, if you have 2 answers that contradict each other, one of them is the correct one. So that should be a clue. If the units are, they're big on they're gonna test you on your units. Know your units for everything. Every unit out there, know it. And a lot of times the question is simply a unit. It's a whole big long question and it seems really hard. It's like, oh my God, how am I going to answer this? Look at the answers. And there might only be one answer with the correct units. It's got to be that answer. So if you know your units, you know half those questions. And remember, you could usually eliminate 2 answers just on the face of it. You read through them and you could imaginary cross off this answer, cross. Okay, now you're down to letters A and C. And now you have a much easier time. Now you get to, without getting overwhelmed by 4 different answers, now you only have 2 answers to worry about. So try to eliminate 2 before figuring out which one is the correct answer. And number 6, there will be many easy questions. Not everything is a trick. I've had a lot of students in the past, we go over the test and they'll mistake the most straightforward question. And they'll say, well, we thought it was a trick. We thought you were, no, it was just an easy question. It was just an easy question with an easy answer. So those do exist. Don't panic because you think it has to be a trick. It doesn't have to be. However, sometimes it is. There are tricks. A lot of times those tricks involve does not, except. In other words, you think it's asking a question in the positive and it's really asking the question in the negative. And so it's the exact opposite answer that you expected. So really pay attention to the wording of the question. I didn't write this down, but we also have to know when to eliminate words. There will be unnecessary information sometimes, and that's designed to parse out whether or not you can really figure it out, the question. But yeah, pay attention. Does not accept. I can't think of any others right now, but you get the general idea. Or very familiar concepts, but they're mixing apples and oranges. And so frame rate and I don't want to say pulse repetition frequency, because that's kind of apples to apples. Frame rate, and then I'm just looking at a note right here, and the Nyquist limit. So Nyquist limit is your pulse repetition frequency divided by 2. That's Nyquist limit is when you have aliasing. You go beyond the Nyquist limit, you have aliasing. How many of you remember that? Frame rate is related to the pulse repetition frequency, but it's a little different. So both of them are related to pulse repetition frequency. And so they're both could be very familiar, but not apples to apples. And so it's very easy to kind of get confused with those. But sometimes those look like a really easy answer or a really easy question. And it's apples to oranges. Never take anything for granted, but then don't go changing your answer either unless you know it's wrong. So remember, first impressions, unless you're just completely guessing, then the first impression is probably no good. But your first impression usually is correct. I encourage you to take every minute they give you and go back and reread questions. Or if you've gone from, on question 100 gives you a hint about question 50, then by all means go back, reread it, and okay, and change your question. But think twice. I don't want to say never change your answer, but I want you to think twice before changing your answer. Okay. So I think I have some hard questions. But we're going to work through them and see if we could. You either answer because you know it, and that's easy, but I have a feeling the demodulation process might not be at the forefront of your brain right now. I just have that feeling. So which of the following best describes the demodulation process? Okay, so let's go over these. Changing the grayscale of an image. Changing the grayscale of an image. You know that you learned about demodulation, and you know it was in the back of the book. It was one of the later chapters, right? Changing grayscale of an image was beginning of the book. So in demodulation and changing grayscale, you might just remember I don't remember demodulation and grayscale being in the same chapter. It just doesn't seem right. Changing the frequency of a signal. Okay. And I'm trying to come at this from a point of view of having difficulty remembering the entire book, which I do, by the way. Changing the frequency of a signal. Okay, once again, frequency of a signal in demodulation, frequency of a signal in demodulation. It just doesn't seem like that was the same chapter. And it seems like demodulation was something else, Whereas changing the frequency was, well, there's a frequency button, and why do I have frequency? Well, broadband, and yeah, I think we could scratch that one out too. So now we're down to 2, hopefully our logic is correct so far. Which of the following best describes the demodulation process? Changing the form of a sound pulse. So all of these are changing the form of a sound pulse, or changing an electrical signal's form. So between those two, if you're not sure what demodulation is, this might be a 50-50 choice. I'm trying to think of what other technique could I use here? Modulation process. Changing the form of a sound pulse. So, okay, I think we can work this out. What does changing the form of a sound pulse mean? Okay, well, a pulse could have a different, we could change its curvature. In other words, its focal point. I don't think demodulation came up in the focal point chapter. We can change a sound pulse by strengthening it. That doesn't sound like demodulation. Strengthening a pulse or weakening a pulse doesn't change. Sorry, my phone did something. I wasn't sure if it was you guys. Okay. So I'm starting to have doubts on letter C. On letter B, D, changing the electrical signal's form. I might not remember what demodulation is, but dang it, if that doesn't sound like the same chapter. Electrical signal and demodulation. I'm going to choose D. And I'm right, yay. So just a reminder, by the way, demodulation is basically taking the alternating current. Here's my baseline, and this is voltage, not sound waves. They represent sound waves, but it's your voltage. And then demodulation first takes everything, takes all of the bottom stuff, puts it on top, and then it smooths it. So you have smooth. Electronics don't like messy electrical voltages. So we kind of answered that question without really knowing what demodulation is. Not 100% remembering what it was, but we know. It's literally nonstop with these marketers. We were able to kind of think, all right, demodulation, end of the book. It seems like that was end of the book. And once you start saying end of the book and considering changing the grayscale and the frequency and the form of a sound pulse, that all happened a little bit earlier in the book. And I don't remember demodulation being anything there. So it's got to be D. All right. And that's a hard question. I wouldn't be surprised if almost all of you didn't quite get it. I guess I need to make that smaller. Okay. Second hard question, which of the following is a typical value for the amplification of a signal by the receiver? Okay. We've got a couple of things. We have a couple of clues here. One clue is watts, decibels, decibels, watts per centimeter squared. You guys probably remember that that's intensity. And amplification and intensity, not really related. Now watts, that's, so the other, so we have 50 to 100, 50 to 100, minus 50 to minus 100. Okay, that is, you know, watts kind of makes sense. If you're amplifying something, you could amplify it by a number of watts. And let's say you just, gosh, watts, decibels. I can't remember. Well, here's another clue. Minus 50 to minus 100 and 50 to 100. Now it still could be letter A. It could be. If you don't know if it's watts or decibels, that could be. But B and C kind of give us another clue. These are opposites. These are basically one saying it's north, the other saying south, and one saying east, the other saying west. These are opposites. Now you could remember, as you sit there and think, like, oh my gosh, amplification of a signal, amplification of the signal. What's the difference in value between the beam and the echoes returning? What multiplication factor? Do you guys remember? Millionfold, 10 millionfold difference in the strength of the beam versus the echo. So when we talk about amplification, now I realize we're not electrical engineers. We really don't even know what 50 to 100 watts really means. I don't really know it. But I do know that amplification is huge. The actual amount of amplification is gigantic. And we have two answers that are basically opposites. So let's cross out a couple, and we're down to B and C. Minus 50 to minus 100, that actually sounds more like attenuation. Attenuation is always negative. And we could be talking about millions of decibels of amplification, and 50 to 100 decibels does actually qualify that because it is logarithmic decibels. Once you get into the 50, 100 range, we're talking about gigantic numbers here. So that's attenuation. Let's go with that answer. So hopefully you see that you can answer these questions without being able to memorize everything in the book. It's better if you do, but I don't expect you to. Well, I'd like you to. So which of the following is a typical value for the amplification of a signal by the receiver? We know we're not talking about intensity. At least we hopefully we know that. Could be talking about watts, but boy, amplification is in the millions fold, million fold. So hopefully that helped. But also we also had this opposite, which kind of said, it might be one of those two. So Not necessarily. I don't want you to die on that sword and then go yell at me for giving you bad info, but it might help. All right. Question 3, which transducer system is most likely, oh yeah, to have the longest delay in its TGC curve? What are they asking? Kurt never talked about longest or shortest delays. Well, that's because I didn't really need to, but the question's asked in such a way as to really, you have to understand what they're asking. What they're asking is stuff that we have actually covered, but they're saying it in a very different way. So which transducer system, okay, is most likely to have the longest delay in its curve? Most likely have the longest delay. Let's hold off for a second on the longest delay, because we have to think about what that even means. But before we think about what that means, let's look at the answers. It's just, okay. Just didn't look right. Weird A. 5 megahertz linear array, 2.5 megahertz annular array, 7.5 megahertz mechanical transducer. It's not an array because it's not, it's one element. And a 5 megahertz annular array. Okay, well, let's look at the transducer itself. We have a linear, an annular, a mechanical, and an annular. This TGC, time gain compensation, gain. Does gain have anything to do, at least in our studies, with the type of transducer? Or is it more likely to have something to do with the megahertz? All right. So we have 5, 2.5, 7.5, and 5. Ugh. Well, let's look at the outline. Well, we could look at, there's a 5 and a 5, and a linear and an annular. But TGC, remember, that's the time gain compensation, that curve that kind of does that invisibly, and it's remember, that's, you have to know something, right? That's how much gain per depth, per centimeter of depth is given to the system. And we have control over that. It just doesn't seem like the transducer itself, the type of transducer anyway, has anything to do with that. It seems to have to do everything with megahertz. Because of attenuation, right? Time gain compensation has everything to do with attenuation and mitigating attenuation. So, now we could look at, we have a couple of outliers here. We have a very low frequency and a higher frequency. Not exactly high frequency, but a highest frequency. We have the lowest frequency and the highest frequency. I'm betting on one of these at this point. Okay, so now we have to go back to the question, and what exactly are they asking? The longest delay. All right, well, now we just have to look at the English language and think of what a long delay would really mean. Okay, go down, get away, go away, go. So here's my TGC curve that I just, drew. And if you guys remember, there's actually, if you draw it a little more angular, there actually was something called a delay here, but you might have forgotten that. But what's a delay? A delay is something that you wait for. Well, if you think about, does a delay mean that you start high and then end low with your TGC curve? Or would a delay be something where you don't even use it at all until deeper? That's a really tough one. But if you parse out first the longest delay, that threw me. I mean, I was like, whoa, that's a different way of saying this. And so I had to stop and think about, what is it actually asking me? And so then you could look at this and say, well, my eyes went straight to the megahertz, but you could also look at the actual type of array and say, you know what, that doesn't matter. We never talked about that mattering in TGC. We only talked about, well, it's gain. So in any case, that's kind of working that one out. That's a hard one. If you don't know what they're asking, that is a hard one, and I wouldn't blame you for not knowing. Well, I would blame you. Okay, true, false. People hate true and false, which is really it surprises me, but students seem to hate it. True or false, the sonographer can make an image of uniform brightness by adjusting both the output power and receiver gain. Well, yeah. I mean, the sonographer can make, in other words, adjust, can make an image of uniform brightness by, well, yeah, there it goes. There's adjusting output power and receiver gain. Yeah, right? You turn up your power, you change the brightness of the screen, you turn up your gain, or vice versa, turn up, turn down. You increase the brightness of the screen. Absolutely. The sonographer can make an image of uniform brightness by adjusting both output power and receiver gain. What are we missing? It's not true, is it? What word did we fail to notice in this question? Let me put it this way. What word did I fail to notice when I quickly read the question? Uniform brightness. Sometimes there's extra words in there that are useless. Sometimes there are words that are very descriptive. We take the word uniform out and we say the sonographer can make an image of brightness. All right, that'd be a little bit of an awkward sentence, but brightness by adjusting both output power and receiver gain, then the answer is true. But uniform, that's referring to the TGC, and the question asks nothing about TGC. That's really tricky. All right. Last of the questions. It's only 10:42. Ugh. Well, I got some other stuff to talk about too. True or false, an ultrasound system with a longer pulse duration will generally have better temporal resolution. Oh boy. What did I say about apples and oranges? So familiar, but wrong association. So it is very easy to quickly answer this question incorrectly. An ultrasound system with a longer pulse duration will generally have better temporal resolution. These are, I guess what I'm trying to say is apples to oranges. The pulse duration in microseconds there. And temporal resolution, which is really more related to how many pulses in a second, are not related. So that's a false statement, simply because it's an unrelated association. But it's very easy to quickly read that and say pulse duration, temporal, kind of a false promise of, oh yeah. But they're not. Okay, I think I have some stuff on mind dumping. I also have some stuff there on. Yes, okay. So this is not meant by any means to be exactly what you need to do. You memorize the equations you think are best, and we can go over. I could pull out every equation in the book, and I'll do that next time, maybe tomorrow. I'll go over every single equation in the book, and we can talk about the most important ones. All right. Forget what I wrote right there for the moment. Just look at that. So I suggest this triangle. If you like the triangle. If you don't like the triangle, then write the basic equation for frequency or wavelength. But they're all the same equation, right? It's just, you just go around in a circle. Now I wrote in my triangle, speed of sound, constant, frequency times lambda, you could lambda times frequency, doesn't matter which one's first on that bottom row. And then I realized, you know what, Kurt, you're going to talk to the students about units and knowing their units. So it's like, oh, okay, well then I went ahead and I put millimeters per microsecond over here, and maybe maybe I should do 1.54, just to remind myself that that's a constant, always the same. Frequency is in megahertz. Remember, by the way, megahertz and microseconds are reciprocals, so they cancel. And millimeters. All right, so by having this, this is by far the most, this equation, absolutely, you have to have these equations down. I'm just gonna write it really small here. And those two for sure, this last one, I mean, no, but you can derive that though, but I'm gonna scratch that one out. Okay. Absolutely, positively, you gotta know that one. And I was just flipping through the book. So this is not, once again, not to be considered, oh, this is all I need to write down. No. I was just flipping through the book this morning. Well, I have an assignment for you guys too. That will help. Okay, one thing to think about. Chances are, and I'm reading over here now, chances are you will not need frequency element calculations. I'm just guessing that probably not, maybe one question, which one question is one question, you want to get it right. So don't bother writing this out again when it's the same equation, right? You don't need to write this. If you just write this down, and if you get to the frequency of the element, not frequency in the body, but frequency of the element itself, and how is that derived or something. Then you go back and say, okay, well, now let's use a different color. Now that was like, oh gosh, I don't know, 4 to 6 millimeters per microsecond. Frequency is still megahertz. And lambda is, well, still in millimeters, but it's now 2 times the thickness of the element. And so now you didn't have to memorize both. You only had to memorize one, and only add, probably only this actually, because they're not even going to have you figure out the answer. You might need that, but probably not. I'm guessing that's a question you will not be asked. All right. And then I was just flipping through the book and I saw attenuation and attenuation coefficient. Okay, so attenuation coefficient, yeah, you should know. You should know that, because this is easy math too. If they say the frequency is 10 megahertz, what's the attenuation coefficient? 10 divided by 2. You don't need a calculator for that. I don't even need a calculator for that, which is quite impressive. So remember the attenuation coefficient. That's the attenuation every single centimeter. Oh, did I? Idiot. No. Attenuation coefficient does not have a centimeters. Okay. So if you know that, do you really need to write down attenuation? Maybe you do, maybe you don't. So attenuation, I have to write really small here. Let's do a different color. Attenuation is equal to the attenuation coefficient, in other words, right there, times depth in centimeters. Yes, centimeters. And there you go. So you don't necessarily have to write down the attenuation formula because the attenuation coefficient is probably the harder part to remember. Attenuation. If you can't remember the attenuation formula, be like, oh my God, it's attenuation coefficient. Well, just slow down and think, what are you trying to figure out? How much the sound beam weakens with depth? Oh yeah, right, depth. Okay, there you go. Trying to say is stay calm. If you stay calm, the question you're asking, as long as it's in somewhere in here, the question you're asking will eventually seep back into your brain. And you might get an attenuation question and you draw a blank, like, oh my God, I can't remember the attenuation equation. Move on. And that one, you might not even want to answer the question, but mark it and move on. Trust me, 10 questions later, your brain's going to say, that's what it was. You go back to it. Range equation. Great example. I was like, oh my God, Kurt, what's the range equation? Well, let me just do something. You're trying to find the range of the moon from the Earth. C is actually the speed of light. You fire a laser to the moon. There's actually the astronauts put a little mirror up there. It's a special kind of Fresnel lens that always bounces back to whatever hits it. So the mirror bounces the laser back, and you know how fast, whoops, you know how fast it was, and you've timed it, your range finding machine. Oh, and by the way, in that case of finding range by bouncing a laser off the moon and back, or by bouncing ultrasound off of the gallbladder and back, that's two-way street. So remember to put always remember to put your 2 in there. So that could be a good one to know. And it's in millimeters. Why is it in millimeters? Well, times time in microseconds. Aha. Microseconds cancel out, you got millimeters. So if you can't remember, oh my gosh, is this in millimeters or is this in centimeters? Look at your equation. The speed of sound is normal. I know sometimes I put it down in meters. That's just because that's what the SPI is going to do too on you sometimes. But normally it's measured in millimeters per microsecond. And time is in microsecond. So, bam, your answer is going to be in millimeters. Related, in a way, I would memorize the pulse repetition period. And we talked about this recently. Pulse repetition period, remember, is the distance in centimeters times the 13 microsecond rule. Why? Because it's in centimeters. Well, that's not only the reason why. But bear with me here for a second. If you put okay. Sorry. If you happen to put 13 time in, yeah. If you happen to put 13 here, you get 10 millimeters, which is the same as 10. Oops, I'm sorry. 1 centimeter. That's why we have a 13 microsecond rule, because we want to know how things go and how far sound goes there and back. And you know saying it backwards. How long it takes to go there and back. In other words, 1 centimeter of depth. And how long it takes. 13 happens to be the number that works. So that is what we use. So pulse repetition period. The nice thing about if you know the pulse repetition period of something, you know the pulse repetition frequency. You just put a 1 over it, do the inverse of that. Axial resolution. I just threw this in here. Spatial pulse length divided by 2. The number 2 is a common feature. In the case of axial resolution, it's a little bit different. Well, actually, it's different. It's different. Actually, different for all 3 of these. But spatial pulse length divided by 2 is your axial resolution. I know we had difficulty understanding that. That's okay. Just worry about this. Well, just memorize, just spatial pulse length divided by 2. And that's that. In other words, another way of saying it is 1/2 the spatial pulse length. So if your spatial pulse length is 2 millimeters, your axial resolution, your ability to see 2 different objects in line, is down to 1 millimeter at best. And I think this might be the last one I threw in here, Doppler. Remember, guys, chapter 18, chapter 19, we kind of more or less covered in vascular. It's physics, you know, it's all from the same book. So that is part of our studies. Doppler equation, once again, here's a number 2. In this case, it's because the 2 is in there because there's 2 Doppler shifts. The red blood cell is going in, let's say it's a positive Doppler shift. Doppler is coming from one direction. The red blood cell is coming the other direction. I shouldn't say Doppler. The beam is coming from one direction. The red blood cell is coming from the other direction. So they're coming at each other. In other words, it's going to be a positive Doppler shift. The first Doppler shift is that the red blood cell is traveling towards the sound faster than it normally would happen. And so you're hitting the peaks faster. That's shift number 1. Shift number 2 is now it is producing sound. The red blood cell is, we call it producing sound. Even though it's reflecting sound, it's still a producer of sound. It's producing sound, but also chasing its own wave. And so subsequent waves are closer. In other words, higher frequency. So that's why there's a 2. There's 2 shifts. Well, velocity. And this is what the computer actually solves for, is the velocity of blood. But it only does that after it's solving for the Doppler. Times the frequency. So by the way, remember, frequency of the Doppler, I keep saying Doppler, frequency of the sound beam. So if I increase my frequency, I increase my Doppler shift, but I don't change my velocity because it's all built into the equation. Velocity will not change if I change my frequency. Does that make sense? I actually increasing my Doppler shift without increasing my velocity. What does that mean? Well, the equation, when you rewrite it, solves for that. It says, yeah, no, we understand your Doppler shift might be shifting more because of a higher frequency, but now the higher frequency, I believe it goes into the denominator so that the velocity will remain the same. All right, anyway. Cosine. I remember the biggest number. The biggest number is 1. The smallest number is 0. That's the cosine. That doesn't mean the theta angle is 1 or 0. That means the theta angle could be 45, 60, 70, 20, all those different. But any of those numbers, when you do a cosine of them, they fall between 1 and 0. If you have a 1 in this place, that is the maximum Doppler shift. That means the blood is either traveling directly towards or directly away from the transducer beam. In other words, a 0 angle. If you have a 0 here, that means that theta angle was 90 degrees, and 2 times velocity times frequency times 0 is 0. When you have a 0 in an equation like that, everything else is 0. Now, realistically, As hard as it is to get a super great Doppler angle, it's also very hard to get a truly 90-degree angle. So it doesn't happen all that much. Okay. Divided by the speed of sound. And this is in velocity and, yeah, that's going to be per second. That's in megahertz. Yeah. All right, 11 o'clock. Okay. Well, I've got some announcements I actually wrote out here. Oh, okay, I did one more. You know why? Because I was flipping through, and what did I find? Yet another 2. Pulse repetition frequency divided by 2. What is the Nyquist limit? When you exceed the Nyquist limit, color Doppler, spectral Doppler, you get aliasing. And that's by the pulse repetition frequency divided by 2. When you exceed that, you get aliasing. So that's a limit. Don't go over the limit. I got pulled over the other day from a stupid, it used to be my wife's car that Audi is so stupid fast. But you know what I was really nice to the guy. I kept my hands up, gave me a warning. Kissed butt. All right. Oh, announcement number 1. Just when I was trying to get on the Zoom today, because you can only schedule out so many Zooms, and it's like just under the length of a semester. I noticed that last semester. I'm personally out of Zooms, so I think I could go back and reopen other Zooms and it still works. So that's what I actually did today. So we might not have a new Zoom number, but if so, I'll send that information out to you. So let's see. I'm out of town on the 20th. That's a Friday, right? This update, I am going to scream. Okay, yeah, 20th is Friday. So asynchronous on Friday, which means it will open up at 7 o'clock in the morning. You could watch it any time of the day. I'll also put out another. You guys saw there's an asynchronous today, tomorrow, today Wednesday for lab. The asynchronous for today and Wednesday is that guy. I would suggest going through all of his videos if you haven't already. I can't remember his. I don't have it up right now. Anyway, he's great. He's a real bright guy. I'd suggest going through all of his videos. But this video was the console video. The SPI no longer has a console question. Well, a question with the console on it, because I guess people, I don't know. I didn't think it was that confusing, but people found it confusing. A lot of complaints about it, so they dropped it. That doesn't mean those questions are not asked. So they'll still show you, like on this video, he has a liver and you guys don't know what a liver looks like, but you do know when something's way too bright, right? And so the whole screen was too bright. And he starts to go, I stopped watching because I had other things to do, but he starts to go over, kind of the way to think about the questions and then ultimately what the best answer was for that question. Even though you don't have the console, you'll still have the question. And so I still think it's worth going over what he has there. So that's today's and Wednesday's asynchronous assignment. I'll put another one out. Practice final. We need to do that. I thought about Friday on the 20th, but I'll give you guys over the weekend. 23rd is a Monday. All right, I'll leave it open. I'm just going to tell you right now, I'll leave it open. Guys, this is a practice final. This is like, do you know it or do you not? In other words, I don't want to find out that someone took it at 8 o'clock in the morning and then their friend aced it at 12. Yeah, because I know that's happened. I'm not blaming you guys. I know, quite frankly, I know for a fact it's happened in other classes. So you understand, I just don't want that happening. I could probably, no, I might as well keep recording. I'll go ahead, I'll leave that open. Please, just please do your own work on the practice final. 24th, 27th, I'm going to create some more asynchronous assignments. Melissa's going to be looking in after you. I'm sure she'll have a Zoom with you guys, but she's honestly, she's not prepared to teach this class. Oh, by the way, do not be afraid to contact me while I am out of town. Texting is probably best. Texting is probably, all right, now I'm really going to regret that because I actually have, there's a few people in schools, like, I don't even know where they are, like other parts of the country have signed up for my YouTube channel. And so now I'm going to start getting texts from, I don't know, California, which by the way, I never answer California. It's a foreign country. Anyway, so I'll create some asynchronous assignments. I also have a project. Projects in the past have been pretty big, and I've had a lot of complaints about them. So I decided not to do my old project after lots of complaints that it was too much work. So I have an easy one for you. And I have a valuable one for you. I made one of these for myself. I'll try to find it, or I might have an image of it, and I'll show you guys. And I want to see what you've created. One page, single-sided cheat sheet. Now, when you do this, you're not going to be able to do it on your first try. You're going to think you got it, you're writing small enough and everything, and you got it all organized, and you get to the end, it doesn't work. You might want to do it on a computer, and that's fine too. Like personally, I would do it on this program. But if you could do it on Word. But I want to see you guys with a good cheat sheet. I think written out is probably best, actually. But do what you want. You're going to do it, and I am strongly suggesting, I'm not going to ask for every copy. You're going to do it over and over until it's perfect. All right. By doing it over and over, not mindlessly, but thinking about it, it's going to be practice. You're going to start remembering a lot of stuff. Remember, you can't bring the cheat sheet into the test. But what you might be able to do is, once you really have that cheat sheet down, during the test, during your mind dump, you just kind of close your eyes and think, okay, I wrote that down. I wrote that down right here. Can I picture it? Well, I can't. I have aphantasia. I can't even picture my wife. She's got her headphones on. She can't even hear me, but it's true. I can't. So it's a bit of a, weirdly, it's sometimes an advantage to my memorization. But anyway, going off point here. You go through and you're like, yeah. It's a third line. What did I write? Axial resolution is yeah, SPL divided by 2. Okay, yeah, right. So if you have this cheat sheet really well made, so in the cheat sheet, equations, the fundamental equations, the one at the top of this sheet that I showed you, and all the hard equations. They whoops. Speaking of brain farts. Z2 minus Z1, Z2 plus Z1 squared. Why can't I think of impedance? Anyway, those equations that I can't remember either, because guess what? I have aphantasia. I can't see it in my head, so it makes it a little more difficult. Which is part of the reason why I blank out. One page, single-sided cheat sheet. Yeah, okay. Anyway, I'll write that down. Because I have to actually create an assignment out of it. So I'll write down some parameters and hopefully give you an example of what I've done in the past. So, and you know what? I might just build another cheat sheet myself. And I don't really have time. But anyway, I need that done. When is it going to be due? It's going to be due Monday of finals week, whatever date that is. Monday. All right, so that is your project. Important we get that done. All right. Any questions?